Thank you for the introduction. My name is Reza Nejabati. I'm a professor from University of Bristol. You saw from Michael some advertisement from University of Bristol about the quantum computing, but my group does the networking part of it. So Bristol is pretty big in terms of the quantum research activity. Let's move on to my talk. Let's see if I can work with this. Yeah. So as I said, I am from University of Bristol and lead a large group that works on the quantum networking. What I present today is a result of the research that we did in general in UK and in particular University of Bristol as a part of the UK Quantum Technology Hub. UK government has funded quantum program through 4 major national hubs during 2 phases of the each phase 5 years time, last 10 years. And the second phase is coming to the end in 2024. But and one of those hubs is focused on the communication networking. And I am presenting that part of that. So you see the objective of this quantum communication hub, which is a large national flagship program, is to basically collaborate between universities and researchers in UK and industry, basically to access development of the scalable quantum communication, both in terms of the user and also distance. We have done, as I said, 2 5 years so far, and we are mainly focusing. We started from point to point now, mainly focused on dynamic quantum networking and scaling quantum network in terms of the number of the users and more application. And toward our future roadmap, we are moving beyond security and to focus on how to connect the quantum computers together. So that's would be a part of my talk today. So the Quantum Hub has a large number of partners, both industry and academia, as you can see here. I don't go through that, but let's look at it. Why in the hub in UK we decide to go beyond the point-to-point security? If you look at the quantum technology, basically the application is for security, obviously. It's for computing, you have seen it, and also sensing. You can get a great advantage in terms of quantum advantage in terms of sensing. Now, if you bring the quantum network to this picture as well, and try to connect this to the quantum network, and also add things that the classical internet does, I mean multi-tenancy and multi-user, then what you can achieve with that, you can create a quantum cloud computing, create a quantum data center, the way that you can see Microsoft, Amazon, and so on are moving forward. And also you can get a good advantage in terms of the sensing with the quantum distributed quantum sensing. So this is why it's important to look at quantum network in more generic terms rather than just providing the security. So if you look at what's happening across the world in terms of the real-life testbed or real-life networks that are beyond the lab, which is outside of the lab, these are the samples. It's increasing on a yearly basis quite a lot. But nevertheless, still, what is common among all of them are point-to-point and fixed. Majority is for security. There are some that look at application beyond security, but nevertheless, point-to-point and fixed. Although you can see some of them, for example, Madrid one or Vienna one, they resemble a ring or a mesh, but still fixed point-to-point connection. What in UK have done is quite unique worldwide. We have a west coast to east coast of the UK. Comparison to the other countries is very small, around 700 miles from Bristol to Cambridge. Connected with the build a quantum network. So the long distance one is basically done with our industrial partner Toshiba between 2 cities of Cambridge and Bristol, which you will see a presentation later on. However, what is very unique inside the both cities, Bristol and Cambridge, in collaboration with 2 universities, Bristol and Cambridge, we have a dynamic fully mesh quantum network. So we can do the in Bristol particularly, we can our fiber carry classical information and also quantum information in the same fiber. We can route our quantum channel same way that we route our classical channel from any point to any point across the city. The city was very small. The other thing is that you can see at the bottom of the picture, we have connected to the other facility in the city. For example, our telecom infrastructure, which is the 5G or more advanced version of 5G, research version of the 5G, is also connected to this. We can do demonstration application like a security, quantum security for 5G, or do the industrial, for example, using industry partners to connect remotely to our quantum computer that comes to the city. I'll go to that later on. But this is nevertheless is one of the most advanced real field testbed in the world. Now, in Quantum Hub also, in 2024, we will launch our CubeSat, which is a satellite for QKD in partnership with a couple of countries, including Canada, to have our intercontinental and intercountry communications for QKD. So let's go back to this one. The unique this we have in the real life test, which is live. First of all, it does a dynamic switching. The dynamic switching is enabled. What you can see if my laser pointer, no, doesn't work. Okay. Yeah, here it is. We develop and design a quantum router or quantum what we call ROADM. It does the routing of the quantum and classical channels. So in each node is equipped with that. Also, to be able to control this, which I go later on a little bit to that, and also have our classical and quantum channel in the same fiber, we have developed quite extensive machine learning techniques and AI. Basically, the whole network is controlled by AI and machine learning to be able to manage this. Now, these are the unique feature of that test. One is a quantum router, which I mentioned about that. The other is machine learning techniques to allow coexistence of quantum classical channel. Is software defined, completely controlled by software like a classical telecom networks. It provides the real life security showcases, for example, 5G, as I told you. And this is the basically logical picture of our quantum ROADM, if you like. And these are the machine learning techniques. I go a little bit more detail in each of them. The other thing that we do in UK, we try to look at the specialized fiber, how they affect quantum communication or quantum channel transmission. UK is very good in building new type of the fibers. I mean, one of the pioneers. What we have in UK, we have Southampton, which pioneered the hollow core fiber. With hollow core fiber, we did some tests, and essentially with hollow core fiber, like you are transmitting the signal in a vacuum. So there is no effect. You can do whatever you want with your quantum channel at any number of channel, and you can launch into the fiber classical channel at any number of channel. Doesn't affect each other whatsoever. So that's something we have done this. The other thing is we are looking at the free space communication as well as fiber. So we see that how much we can put in close distance to each other spectrum-wise, classical and quantum channel, and launch the free space. So we have done a lot of free space communication with University of Oxford together and that. So these are also non-fiber based communication we have done. Now, last few years we have started to look at the entanglement, how we can use entanglement to basically our network support entanglement, dynamic routing of entangled channel. So we can use it for security, and also we can use that to build the knowledge and expertise to connecting quantum computers. Entanglement give us a capability to scale our network quite rapidly and significantly in terms of number of user and nodes. Here is our entanglement. We have basically a high power laser injecting the signal to a crystal, a specialized type of crystal. Is public knowledge. You can see it's published. Nothing rocket science there. However, what it comes 2 photons for every single photon. You get 2 photons at higher frequency, lower power, which are entangled together. And then with this type of source, we can generate the broadband signal. So we can full telecom band of the spectrum. We can generate a pair of the channel are entangled together. pair of the photons. So, for example, these two color-wise they are entangled together and they are covered the telecom range. So if we push that to our switch, so we can basically direct our entangled photons to any two nodes that we want. So we can create an entanglement relationship on demand dynamically with any two nodes. This is the complexity of, I want to show that the complexity is on the lab, so it's nothing that you can go still to the field, but that's how it in the lab look like. And then what we did, we tried to put that in a city of Bristol, center of city of Bristol, which is a small size, and try to show in the field that we can do 8 entanglement relationship between 8 different users for various applications, including QKD. For this setup, we end up with the 8 node and 30 wavelength that are entangled together, 30 channel that are entangled together. There is a 2.6 million scenario to optimize for each reconfiguration, which is quite significant, assuming that if you want to scale your network larger scale. So that's why we develop our machine learning techniques that I showed earlier. Is basically a neural network base that completely control this. It's humanly is impossible to dynamically control this. It's going to take each reconfiguration of setup few months to organize it. So that's we do it quite successfully with machine learning. So this shows the machine learning result. I mean, that's interesting. I know it looks complex, but it's not. So each stage shows a different reconfiguration of the network, entangled network, and the thickness, it shows the quality of the channel, if you like, for the security in this case, quality of the entangled channel. And the green and red line shows the difference between the experimental result and the predictive result that we got from our machine learning techniques, which completely match, which is quite amazing. So that shows that our machine learning can predict the result quite well, and we can control it with that. Now, moving from the security now, this is something that last 1 year or so we are focusing. If we want to build a warehouse scale distributed quantum computing, that's something that is coming, is essential in my opinion. The reason is that a useful quantum computer that can do useful thing with it is the 1 million qubits. I mean, you can ask a lot of quantum computing vendors are here, startups and big vendors. What is the roadmap for achieving this? It's quite difficult, and that's the minimum you need to do something useful. So, and scalability is a big issue. One way to scale the same way that Amazon and Google, they scale their data center, create a small server, connect them with the networks. So if you have a few qubit processor, which is available now, you can go and buy, there are a few of them in the exhibition. Imagine that there are a few hundred qubits, which is very possible to come in the next couple of years, and then connect them in a warehouse scale control environment using the network, entangle them together, then you can see a way to achieve more than 1 million, at least a possible way to achieve more than 1 million. So that's why we are looking into this. So however, connecting two quantum computers together, a quantum computer normally you have seen in the presentation in the morning that it has a quantum processor and has a classical processor. If you want to connect two quantum computers to do distributed processing, you need to entangle them together in a simple form. Entangling together means that 2 of your qubits, which are very precious, there are few qubit processor, are being sacrificed for communicating to processor. So the penalty would be you need to sacrifice some of your qubits for communications. Now imagine that you have 20 of them are connected together in a fully meshed topology. You can see how many qubits you have to sacrifice to communicate to them. So to avoid this, to make it more efficient communication between your processor, we are also using our entanglement distribution switch that I showed you earlier, enhanced version of it to connect this processor together. It gives you a few advantages. You need to consume less qubit for the communication, and also you can share other sources that are expensive, like a Bell state measurement and so on for your computing processor. Now, our vision is that to build such a data center that is a few qubit processor. They are divided or categories or clustering into the pods, and then they have a classical network and also a quantum network connecting together. So this allows you to create very interesting properties. You can connect them or create any arbitrary graph for your quantum processor to connect. So if you go to the quantum algorithm, the people that develop quantum algorithms, they used to the fixed graph, fixed processor architecture interconnect inside the qubit interconnect inside the processor. If you give them opportunity to reconfigure the qubits interconnects, gives a potentially can give an advantage for developing the subroutine or algorithm quantum algorithms. So that's what we are looking to create a new type of the compilers and algorithm for the distributed algorithm that can work with the dynamic graph of the qubits interconnects. Sorry, just one more. So I have to see how to go back. Here it is. Okay. So the challenge is that how to create a distributed quantum algorithm. So we spent quite 6 months to be able to basically break up a part of the Shor algorithm, which is here, to run to 3 qubit processor in 3 time slots. So there is a 3 parallel chunk in 3 time slot, 3 series as well. So to run them in a few qubit processor, and then try this and other algorithms as a similar way with reconfiguring the quantum processor in different topologies to see how it behaves. So the challenges that we face takes a lot of time to break this quantum algorithm to a distributed version based on the topology and find what is the optimized topology for it. Then network plenty loss is become a big problem here. Also, when you do the Bell statement measurement between 2 processors, the synchronization become important. You need to go in femtosecond regime synchronization on your measurements, so which is difficult to achieve. We are achieving what is possible at the lab at the moment, and then synchronization as well. Now we have a large national project between University of Bristol, British Telecom, and Oracle Computing, which was mentioned earlier in UK, and few other universities, you can see the name of them, to try to basically see how we can achieve or solve this problem and create a data center which is made of the quantum processor, classical processor are interconnected together in a dynamic way. So that's basically finish my talk. Thank you.
We do have time for questions.
We are photonic based. We work so far photonic based. We are working with other research groups in UK that on either ion trap or diamond, but on the interface with them, how to convert either microwave or other matter-based qubits to the photonics-based qubits so we can transmit them. Yeah.
Please.
Yes. Yes. Yeah. We work with 2 vendors, very well-known vendors, but they custom built for us. So it is possible, but as long as they have a customer, I believe they will produce it. But at the moment, we are the only customer. Yes. At the moment, we don't. There is no memory, but on the one that we work with the matter qubits, we have effectively a memory that does the conversion as well.